Hello YouTube, this is Moniker127. In this video I'm going to be discussing resistance, electrical resistance. Electrical resistance is any property of a wire that happens to hamper the flow of current. Electrical resistance is measured in ohms, which use the symbol omega. So let's talk about this black line here. And let's call this black line a wire with a resistance of 10 ohms. Now, note this symbol here. This is the Greek capital letter omega, and it's used to denote resistance, wherever resistance is used. And so generally when it's placed on the line like that label, it means from one side of the line to the other. Like from here all the way to over here, there is a resistance of 10 ohms. We need to know this because we need to know in many cases exactly how much current will flow when we place a voltage on a wire, and resistance is something that can be easily measured. So if you apply, say, 10 volts to this wire here that has a resistance of 10 ohms, so you put 10 volts on this side, and as with all electricity, you have to give it somewhere to go, and that's referred to as ground in most cases, because oftentimes it literally is the earth. So over on this side to the right here, I've drawn the symbol for ground, and ground represents not necessarily the earth, but it's a point where all voltages cancel out. So by definition, at ground, 0 volts are present. And we apply 10 volts. There's 0 volts here. Now the 10 ohms, not only will they drop the voltage, and the amount dropped by specific resistance in specific places is not really necessary at this point. All we need to know really is how many electrons and how much electricity will actually flow through a wire in this scenario. So when you put 10 volts on a 10 ohm wire, you'll get 1 amp of current. I generally like to draw current with a spray brush, just to kind of visualize it in a happy, fun way. So zoop, we've added 10 volts, and loop, flows 1 amp of current. And it flows all the way to the ground. And more information will be given on why it does that later. But for now, the important information is that the amount of current pictured here will be 1 amp. If you need to know what an amp is or what a volt is, then check my previous videos on electricity. So 10 volts and 10 ohms will be 1 amp. But what happens, say, if we add twice that? Let's say we decide to put 20 volts on this wire. Now let me change that back to black, because it's back in black. So 20 volts on a wire with a resistance of 10 ohms will cause 2 amps to flow. 2 amps. And I'll visualize that a bit more with a bit more visual aiding bluey dots of science. Okay, so you can see clearly that we've set up our measurements in such a way that 20 volts, 10 ohms, will cause 2 amps. So there's clearly a relationship there. you can tell that when I increase the voltage, the amount of current increased in the same division, in the same amount per the same amount, you see. So this states what's known as Ohm's law. The amount of current flowing in a wire at any given point can be determined by the electrical resistance and the electrical voltage. So the amount of current I, and we generally call it I stands for intensity. It's one of those letters, so it's just stuck around. So I represents current or intensity, but current is measured in amps, A. So A and I, kind of think of them as interchangeable, whereas I represents current in general, and A represents a specific amount of current. Like, you could theoretically use a different measurement for current, the same way that distance is measured both in feet and meters and miles and whatever. Amps is just a measurement for current, and because there aren't a lot of people measuring different kinds of current, there is only one kind of current. Well, that's not true at all, but anyway, there's only one measurement unit for electrical current, so that measurement unit is the ampere, like the foot, and we might measure distance with the foot and label the foot F. We would do the same with electricity, and so we label the actual unit A and the actual property I, so intensity and amperage. So I equals R divided by E. And, oh, whoops, actually, that is very bad. I got that wrong. I equals ER. I should really know that by now. But, so yeah, E is electromotive force, and electromotive force is voltage. That's our electrical pressure, and if you need more information on electrical pressure / voltage, then check my video on that. And it has the same relationship, whereas V is the unit, E is the symbol for the actual force, and the same with omega and R. Omega represents the ohm, and R is the actual resistance. So what this equation states is that the amount of current flowing is equal to the voltage divided by the resistance. And you might think, oh wow, that works out quite well. Why is that? Is that some sort of magical equation placed there by, I don't know, Jesus? Oh no, it's all arbitrary. We decided on it all. It works out so nicely because we decided that what an amp is the amount of current that flows when you put 1 volt on 1 ohm. So it's all by definition. So it's just to make the math easier so that we can do it faster. There's no inherent property of electricity which defines these units, so we just use what works well. So that's all about the measurements. I've done a good 9 minutes on what the units are. But what is resistance? What causes resistance? Now, resistance can be characterized in a few different ways. There is what's known as direct current resistance, and that is resistance to unchanging voltage. Then there's impedance, which we'll talk about a bit later. For now, I'm talking only about direct current resistance, and this is the kind of resistance which you get on DC, but you also get it on AC, but AC has other factors, so it's not the only type of resistance on AC, but it is the only type of resistance on DC. So let's visualize 2 wires here. Let me actually change the color on this other one. And I'll do another color on this one. So, say these are all wires here, and they're not very well drawn wires, I'll grant you, but say this one here is made out of iron. Let me change that to be a bit smaller. Okay. So that wire is made out of iron, and this wire is made out of copper, and this wire is made out of plastic, although when it's not made out of a metal, I'm not sure if you could really call it a wire. But say you have a length of plastic, you have a length of copper, and you have a length of iron, and they're all more or less the same size and shape. If you were to take your handy-dandy electrical resistance meter, which I definitely suggest that you get one, and if you took that meter and placed its leads on both ends of all of these wires, you get measurements that are quite different. And that's because when you have different materials, you have different amounts of electrical resistance, just inherent in the properties of the material. So our meter here looks a little bit like a Game Boy, but just bear with me on this one, alright? It's not the best drawing ever, but I'm sure it'll suffice for our purposes. So I'll go ahead and draw up a nice little wire coming out of the meter. Here, let's label these terminals. Let's label our little wires as plus voltage and common. Which is what they are generally labeled as. So if you were to place your meter wires on both ends of the iron wire, you could realistically expect a resistance of, depending on the dimensions of the wire, let's say it's a really thin wire, and you get a resistance measurement of 25 ohms. Well, on the copper wire, you would get a corresponding measurement of around 12 ohms. Because copper, in general, has a resistance of approximately half of iron. And on the plastic, your meter probably wouldn't even show it, to be honest, because plastic is what's known as an insulator, which means it's not a conductor, not metal. Metal is defined as metal because it conducts electricity. So the plastic would be somewhere around, who knows? Let's call it 1,000,000 ohms, though. I really couldn't even venture a guess at what an equivalent size of plastic would be. And so, oh, I forgot my ohm symbol there. That was the whole point. And so you can see that different materials have different readings, different amounts of resistance, and if you measure them on a meter, it'll show you right here that between these two wires that you've attached, when you hook it up to the iron wire, it'll show a big old 25 ohms there. And when you hook it up to the copper wire, I'm not going to bother redrawing the leads, you get the point. If you hook it up to both ends of the copper wire, you'll get 12 ohms. And the plastic, it won't even show a reading. It'll probably do error or open loop. One of the standard messages when it can't get a reading. Because in order to actually establish a circuit, you need to break what's known as the breakdown voltage of any material, and everything has a breakdown voltage. This is the amount of voltage you need in order to start actually conducting electricity. And with conductors, it's incredibly low, such that it's almost unnoticeable. It can't be noticed. I'm not sure if I said that right, but you get the idea. But with insulators, it gets to be very, very high values. Say, for example, I know that the very, very rough approximate breakdown voltage of dry air is about 3 million volts per meter. So you need 3 million volts for a spark to develop across 1 meter of airspace. And that's really the only breakdown voltage number I have memorized. Generally, when you're working with electrical circuits, you won't even really have to think about it, because you'll be sending electricity only through things that are actually decent at conducting. So with conductors, I think the breakdown voltage is somewhere in the millions or billionths of a ohm, or billionth of a volt. So you don't have to worry about breakdown voltage usually. And so DC resistance, you know that it limits the amount of current, but why does it limit the amount of current? Well, there are the innate properties of the material, but also involved in this limiting of current is temperature. And funny thing is, most materials, when you pass current through them, and they get hotter because the electrons actually slam up against the atoms of the material as they're flowing, and that causes heat. So you'll lose energy on the wires via heat when you send current through them. And this is what actually makes direct current less efficient for long distance transmitting, because direct current has to actually, schlep the whole way from the power plant all the way to the freaking PC or whatever is using it. Whereas alternating current just goes so it doesn't actually travel the whole distance. It's just the pressure that does, not the actual electricity. One interesting fact that I remember hearing a while ago is that the actual speed of electrons are in a wire with current flowing can be measured in units of inches per minute, or maybe inches per hour even. So all of the electricity that you're using came from the wires that are near your house. You're not actually getting power from the electrical company. You're getting electrical pressure, and the actual electrons, okay, you are getting power, but you're not getting electrons from the electrical company. It's using all of the electrons that are local in your house, and in the ground surrounding it, and in the chunk of rebar that they use to connect to the ground surrounding it, and things like that. So I just thought that was an interesting statistic. But yes, back on task. Electrical resistance generates heat. So let's say we have a wire here, and I'll represent heat with a spray bottle filled with red paint. Say that the resistance of this wire is right now, with its current temperature, at 20 ohms. If I were to heat the wire even more, whoops, that was a paint bucket, not a brush, or not a spray can. So I'm heating the wire more. Its electrical resistance would actually increase. So let's say we increased it by a significant portion, so now its resistance will be in total about 15 ohms. I'm just coming up with these numbers. But the general thing to remember is that when a conductor gets hotter, it generally conducts less. It is less of a conductor as it gets to higher temperatures. And I'm not sure if it's technically correct or not, but one interesting way to visualize heat in your head is, say you're looking at an atom edge on here, and it's got the nucleus here, which I'll draw in red. Why red? Oh, no reason. And it's got the electrons, which I'll draw in blue. And I'll only draw one electron for the sake of simplicity, and because I've already used up 20 minutes in this video. But you've got the electron flowing around the atom, and this is the Bohr model. Yes, it's not correct technically, but it is useful. So you have this electron that has a, we'll call it, circular path around the nucleus, and it travels round and round and round, and it follows this path more or less. But as the temperature gets higher, what the electron does, instead of following this nice straight path here, is it starts to wobble back and forth and back and forth. As the temperature gets very high, it wobbles more, and as the temperature lowers and it gets cooler, it wobbles less. And so at any given point where the electron is easy to visualize. So we can never actually know where an electron is, but we can give probabilities of where it might be. And so as the temperature rises, you've got right here where it most often is, and we'll darken this a bit to show that. But as the temperature raises, that what's known as valence gets larger. The areas where the electron might be gets bigger. And let's say it's a very slight possibility it could be out here. And I'm only doing these in dots because that's easier to draw. I don't know if there's any intensity level of the freaking paintbrush here, but just imagine that that is less intense. Here, I can white out some of it to picture that, but I'm sure you get the idea. As temperature rises, this whole shell here, it's kind of a blur of electrons, or what might be electrons, what might be particles, what might be waves, we don't really know. It gets bigger. So the atom in general gets bigger, and when the atom in general gets bigger, more electrons, which let's say are coming from this away. So call that atom, which we just drew, a copper atom, and call this now abnormally large in comparison blue blob an electron, and say that our electron, which is about to power our lamp, is flowing this way because our lamp is over here somewhere, and our power source is over here. So our electron is flying through the copper, but oh no, the temperature is higher, so it's more likely that there will be an electron-electron collision here, because, well, it may miss it entirely if it's so small that it's only traveling along this inner track, the one that's already there, but because it's more possibility that it'll be at this greater distance, our electron will more likely smash into it as it passes through. And again, I don't really know if this is true or accurate, and I can actually almost guarantee that it's not, but it's a good way of visualizing it, and easy way to remember the importance of temperature and conductivity. So yeah, whenever one electron slams into another, it causes a little bit of energy loss, it causes a little bit of friction. That friction is it generates heat. So that is one good way of visualizing electrical resistance heating. Probably false, but you know, a girl can dream. And so that's a general summation of electrical resistance with a lot of information that you really did not need to know, but figured it was interesting nonetheless. Thanks for watching.